So this next part covers pairs of straight lines and homogeneous equations. Again, imagine two lines L1 and L2 in the given plane. Suppose they are given in the form of ax plus by plus c is equal to 0. So in the general form, let's multiply these two equations and expand it out. This will give us a single equation that represents both L1 and L2 in the form of ax squared plus 2hxy plus by squared plus gx plus fy plus k is equal to 0. Also, there's nothing special with writing 2h in front of xy, it's just convention. Now imagine what happens if both lines pass through the origin. Both c1 and c2 will be 0. That will simplify our equation down to 3 terms, as all the terms dependent on c1 and c2 simplify to 0. This is known as a homogeneous equation of degree 2, as all the terms are of second order. This is in the form of ax squared plus 2hxy plus by squared is equal to 0. Now that we know how to represent two lines with a single equation, let's learn how to find the angle between the two lines. We begin by writing the slopes of L1 and L2 in terms of the x and y coefficients. We rearrange for a1 and a2, we plug them into the above equation. We can then factor out b1, b2 from the left hand side, and then divide both sides by b1, b2, giving us an equation where the y-square coefficient is 1. We can then divide both sides of the general form by b. This gives us a by bx squared plus 2h by bxy plus y squared is equal to 0. We do this to match the coefficient of y squared in equation 2 with that of equation 1. And now we can compare both equations to get a by b is equal to m1 m2 and minus 2h by b is equal to m1 plus m2. And then recall the formula for theta in terms of m1 and m2. Square the numerator inside a square root, and then we can write m1 minus m2 whole square as m1 plus m2 whole square minus 4m1 m2. This allows us to plug in the values we acquired from our earlier comparisons. We can then simplify the expression inside the square root and take the LCM of the expression in the denominator. We further simplify the expression inside the square root to get square root of 4 times h squared minus ab over b squared whole divided by b plus a by b. We can keep reducing this until we get tan theta is equal to plus minus 2 root h squared minus ab by a plus b. Again, let's see what happens if theta is equal to 90 degrees. What happens if the two lines are perpendicular? In that case, since tan is not defined at 90 degrees, we take the reciprocal of both sides. We simplify to get a plus b is equal to 0. So L1 being perpendicular to L2 implies that a plus b is equal to 0 and vice versa. Next, what happens if the two lines are coincident or parallel? We plug in 0 into our equation, we simplify, and what we find is that for the case where L1 and L2 are coincident, h squared is equal to ab and vice versa. So these are the only three formulae you need for this section. They work regardless of whether the given equation represents lines passing through the origin or not. So one to find the angle, the other to describe the perpendicularity case, and the last to describe the case where the two lines are parallel. Let's move on to some example problems. 1. Find the single equation representing both these lines. This is fairly easy. All you have to do is multiply the two equations. However, one thing to take note of, the right-hand sides in both equations must be 0. So we multiply the two equations and expand them. This gives us 3x squared minus 2xy minus y squared plus x plus 3y minus 2 is equal to 0. Also, please feel free to pause the video at any given time and try out the problems for yourself. But I digress. 2. Find the single equation representing x squared minus 5xy plus 4y squared is equal to 0. We split the middle term and we factor it out like any other quadratic equation. This gives us y is equal to 1 by 4x and y is equal to x. Find the separate equations representing this single equation. So this is like the previous question, but this time we treat the equation as a quadratic in x. So we apply the quadratic formula. We sub in the values for a, b, and c. So the expression inside the root simplifies out to 100. After simplifying the expression down further, we take the positive and negative as our two cases. We continue simplifying both cases to get the final answer of 2x plus y minus 1 is equal to 0 and 2x plus y plus 4 is equal to 0. 4. Find the separate equations representing x squared minus 2 sec theta xy plus y squared is equal to 0. We again treat the equation as a quadratic in x and then use the quadratic formula. We sub in the values of a, b, and c. We can simplify the expression inside the root, and since x squared theta minus 1 is tan squared theta, we get x minus y whole sec theta plus tan theta is equal to 0 and x minus y sec theta minus tan theta is equal to 0. Next, find the angle between the lines x squared plus 3xy plus 2y squared is equal to 0. So we compare with the general form ax squared plus 2hxy plus by squared is equal to 0 to get a is equal to 1, 2h is equal to 3, so h is equal to 3 by 2, and b is equal to 2. So we apply our new tan formula, plugging in a, b, and h, and simplifying, we get tan inverse of plus minus 1 by 3, where the plus minus represents the obtuse and acute angles. 6. Find the angle between the lines x squared minus 5xy plus 4y squared plus x plus 2y minus 2 is equal to 0. So again, even though this is not a homogeneous equation, because both lines don't seem to pass through the origin, we can still compare it to ax squared plus 2hxy plus by squared is equal to 0. And we can use the comparisons to plug in the values of a, b, and h. We can simplify this using a calculator, and then we get theta is equal to either tan inverse of 3 by 5 or tan inverse of negative 3 by 5. 7. Show the lines represented by x squared minus 2xy cot theta minus y squared is equal to 0 are perpendicular. This is fairly simple. We just make the comparisons and check if a plus b is equal to 0, because that's our perpendicularity condition. And since minus 1 plus 1 is 0, yes, the two lines are perpendicular. 8. Show that the lines representing this equation are parallel or coincident. So again, we make the comparisons, and this time we check for the parallel condition, which is h squared minus ab is equal to 0. And since when plugging in the values, it does give us 0, we can conclude by saying, yes, the two lines are parallel. So for our final problem, we need to find lambda so that the pair lambda x squared minus 5xy minus 6y squared is equal to 0 is perpendicular. We make the comparisons again and again use the perpendicularity condition, so a plus b is equal to 0, to find that lambda is equal to 6. We can plug in 6 instead of lambda into the given equation and factor out the quadratic by splitting the middle term. To get either 2x minus 3y is equal to 0 or 3x plus 2y is equal to 0.